In this video, I'll be talking about the MATLAB script for solving the nonlinear differential equation that we discussed last time. We have a second-order nonlinear differential equation, as you see here, where the nonlinearity comes from the second piece. We have two boundary conditions. Both of them are on the function value. There's no derivative type boundary condition. At x equals 0, I have the function equal 100, or y is equal to 100, and the right boundary where maximum x is 5, I have the function equal to 0. So as we discussed last time, we use central difference to discretize the first piece and the second piece. So the second piece, we have multiplicative term, yi comes from this piece, and then derivative comes from, well, the discretization of the derivative comes from dy dx. There I used central difference on both discretization, the d squared y dx squared, and the first derivative from this table that I posted on Blackboard a few weeks ago. So that's the first derivative, and that's the second derivative central difference approximation. So getting back to here, then what we do is we multiply this by del x squared. We get everythyn on the left side of the equation, and on the right side we have 0. So the boundaries are y0 is 100 and yn, depending on what n is, equal to 0, where my I index now goes from 1, leading to y0 as the left boundary, and yn, where I is equal to n minus 1, sitting on the right boundary. So that's why we have yn equal to 0. Alright, so here is the MATLAB script. I have the tolerance. Domain length is 5. Left boundary, right boundary, maximum iteration for the Newton's method is 20. I start with discretized level 1, which means I have 2 raised to the first power plus 1, which is equal to 3. That means I have only 3 points across my domain. Out of those 3 points, I know 2 of them, the first and the last, because they are boundary conditions. And the only unknown at this time I have is y1. If you think of y0 and y2 being the 2 boundary points, then y1, the middle point, is the unknown. So that means I can go back and solve y1 from here without even actually using Newton's method, because I only have one unknown. There's no system to solve. So you see how simple this is if we have only 3 points across the domain, and that means it's simple if we have discretized level equal to 1, which means low resolution. Okay, so at low resolution, problem can be solved even without Newton's method. Okay, so when we put discretized level equal to 1, then as I discussed, we have 2 points. 2 of them are unknown. So the first one is y0, the left boundary. The right point is equal to yf or y final, which is the right boundary point. And the middle one I can easily solve from here. So basically, if you set I equal to 1, then this is y0, this is y1, and this is y2. Out of these 3, you know 2 of them. You can only solve for y1, which is the middle one. So you plug in yi plus 1 and yi minus 1, and from here you solve for yi, which is this equation. So I'm solving the middle one in terms of the 2 side ones. So by that, I have solved the problem using 3 points in my domain. 2 of them are unknown, and if I put a breakpoint here and run the code, you see at this point I satisfy the 2 boundaries, which is 100 on one side and 0 on the other side, and the middle one, which is 6.89, is the one that I solve for. Okay, so now I'm going to use these 3 values as my initial guess for the next Newton's iteration. So that means now if I increase my resolution level to 2 by adding 1 to it, then the number of points is going to go up to 2 raised to the second power plus 1, and that means I have only 5 points. So now from 2 points we go to 5 points. Now with 5 points, we know 2 of them, the first and the last, so there are 3 unknowns. This one needs to be solved in Newton's method using system of nonlinear equation. So, and you see, the problem is what you put for initial guess if you have a system of nonlinear equation. So for that system, we're going to use the converged solution of discretized level from before, and then solve the Newton's method, or we go over the Newton's iteration. So this is how it works. We increase the discretized level by 1. Now we have a new number of points, which is 5 in this case, when the discretized level is 2. Then we set up our x values by having a vector from 0 to L with n points, which is now 5 points. And then we set up the initial guess. So initial guess is going to be for the new resolution level, which is 5 points. I'm going to have every other point equal to the previous converged solution. Previous converged solution is y old. I have 3 points there. Current y has 5 points. So if I set every other point of the current vector y equal to y old, then it would make sense because I have 3 elements on the right side, 3 elements on the left side here. So then I can do substitution, or I can do the assignment, right? So that's how we used the converged solution of the previous discretized level as initial guess of the next discretized level. All right, I initialize my f vector, which is the vector of the equations in the Newton's method. I set up the Jacobian to be a 0 matrix of n minus 2 by n minus 2. Why n minus 2, why n minus 2? Because out of n points, you know 2 of them. So you're left with only n minus 2 variables. All right, so our initial guess is going to be the previously converged value plus some small perturbation, let's say 0.1. Okay, so we're going to add 0.1 to all elements, and y old initially is going to be the converged solution from the previous discretized level. Alright, now we go to the Newton's method. This is Newton's method. We have to create the f and the Jacobian. And after we create f and Jacobian, we go back and solve the system from page 154 of the notes. Or if you will, actually 153. We solve the system using this iterative method. Alright, we need only Jacobian and f. So Jacobian is h, and f is the right side. F is the vector of equations. So for every f, we have this equation. So this is our f, right? The right side is 0, and the left side is called f. When I is equal to 1, we have this equation where y index starts from 0 to 1 to 2. And then when I is equal to, let's say, n minus 1, then the y index starts from n minus 2 to n minus 1 and then to n. Alright, so I assemble this Jacobian in 3 pieces. The first piece is for the first row. Why first row is different from other rows? Because in the first row, we know y0. When I is 1, we know y0. So there is only 2 unknowns, y1 and y2. For the last row, again, it's different because for the last row, you know yn, you solve for n minus 1 and 1a minus 2. So then again, you have 2 unknowns. For all other equations, you have 3 unknowns, so that's why you have to split the assembly into 3 pieces. First row, last row, and all other rows. So I'm going to go over maybe the generic one, but you can easily construct the other 2. So in a generic case, this is our f is 1 minus 0.05 dx. This is, let's say, yi, and this is, I have w, but in the note it's y. I don't think there's a difference. So this is yi, and then yi minus 1. This is exactly here. 1 minus 0.05 yi minus 1 times del x, so that's exactly what I have there. And then the second piece is minus 2 times yi, and here is minus 2 times yi. And the last piece is 1 plus 0.5 0.05 times dx yi and yi plus 1, and that's exactly what I have here. 1 plus 0.05 dx yi plus 1. So I didn't do anything, I just rewrote this in MATLAB. Maybe you can see line 58 of my code. Now, the Jacobian line corresponding to this f is going to be, you have to go over every element here and take the derivative with respect to unknowns. We have 2 unknowns, yi minus 1, yi, and yi plus 1. So I'm going to go derivative one by one. Derivative of this with respect to yi minus 1, I only have this term left, which is 1 minus 0.05 dx yi, and that's what I have here. So that's the coefficient of derivative of f with respect to yi minus 1. The second coefficient of this row of the Jacobian is going to be derivative of this with respect to yi. So let's look at that. Yi, I have this term, which gives minus 0.05 dx yi minus 1, and that's what I have here. This term gives rise to yi plus 1 times dx times 0.05, and that's what I have here. It's 0.05 dx yi plus 1. So that's the coefficient for yi plus 1. This is the coefficient for yi minus 1 when you take the derivative. And this one is the coefficient when you take the derivative of f with respect to yi, which is 1 minus 0.05 yi minus 1. I'm sorry, there's no y, so it's minus 0.05 dx yi minus 1, which is this piece. And then the derivative of that with respect to yi is minus 2. Derivative of this with respect to yi gives rise to 0.05 dx yi plus 1, which is this term, and this times that, and then the 2 minuses actually cancel out. Anyway, so you can assemble Jacobian. You solve after you assemble the Jacobian, you can solve for the unknowns, and this unknown is going to be the solution in the current iteration. To find the error, you have to subtract this from previously solved unknown in the Newton's method. So that's why I'm subtracting this one from the previous solution from previous step. And then again, this has to be every other one because the dimension of w is actually, I'm not going over every other one. I'm just leaving out the first and then the last element from w because those are boundary conditions. So I'm just comparing unknowns of current w to unknowns that I just solved. And that difference goes to the error that I want to check in my Newton's method. And that's how I check the norm of the old w plus the minus the current one, or current one minus the old divided by the norm of old, and that has to be less than tolerance to converge. After this converges, then our w is going to be now assigned to y, and now I can do the check for whether to stop increasing the discretized level. If the previously, so this is the previously converged solution. This is the low discretized level. This is the this is from a discretized level 1 more than y old, and that's why we are comparing every other point in the current y compared to the y old. So if this difference divided by norm of y old, if this ratio is less than the relative error tolerance, that means I have to stop increasing the discretization level. That's it. So the rest is just to plot, basically save and plot the points. Alright, so after you calculate the relative error, you check it against the relative error. If I run that, you see this. Well, here, so here's the red line is the solution from the low discretized level all the way to blue. As you see, I have about maybe 100 points or so as the highest level. So the level of discretization goes from red to blue. I hope this is useful, and thanks so much for watching.